Hi, this will be just a relatively quick follow-up video to my previous mailbag one where LD from techbox.net sent in this very nice line impedance stabilization network, which is used for EMC pre-compliance testing for, in particular, conducted measurements instead of radiated measurements, which we'll get into. So I thought I'd do a quick video showing you how to do some rudimentary pre-compliance testing with one of these line impedance stabilization networks, or listens, and a cheap bottom of the range Rigol DSA 815 spectrum analyzer. Now, pre-compliance testing is a big deal for anyone, really, any manufacturer manufacturing any electronic product that you want to sell in the commercial market in pretty much any country in the world, at least if you care about doing it legally and correct. And you've probably seen these symbols around, this CE mark and this FCC mark here, and in Australia, this CTIC symbol here. Now, different countries have various standards. The CE standard, this is EMC compliance, electromagnetic conformity. Basically, in the European Union have that standard. In America, it's the FCC. In Australia, it's this CTIC compliance standard. So depending on where you want to sell your product, into what markets, you may have to test your product against these various standards to get this mark on your product. And it can cost thousands to tens of thousands of dollars to get your product tested. So you've designed your widget like this mains plug pack here, and you've done all the proper design rules, and you know what you're doing, and you're pretty sure it's not going to radiate much, and it's not going to be susceptible to outside interference, even if you care. You go to get the thing EMC compliance tested, and fail. You forgot something, and it's failed the very stringent requirements, or very specific requirements, for any one of these particular things. There are more standards than this, of course, and it depends on the type of product, which we won't go into. The details are enormous, but when you design your product, if you fail that pre-compliance testing, not pre-compliance, proper compliance testing, then you'll have to respin your product, or figure out what's wrong first, and then respin your product and get it tested again. And to do that over and over again on a trial and error basis is a real pain in the ass. So any smart company will called pre-compliance testing, and you can do that in-house with, as I said, one of these line impedance stabilization networks for conducted measurements, and a cheap-ass spectrum analyzer, which you can get these days, like this Rigol one. But there are several types of emissions that your product can actually emit, so we have to talk about those quickly, because we're only going to look at one today. Now, I've got this diagram from Wikipedia. Thank you very much, Steel Pillow, because it quite nicely illustrates the four different noise coupling or emissions coupling mechanisms from your device here, which will call the source. One of the major ones, of course, which everyone thinks of when they think of EMC compliance and things like that, is what's called radiative emissions. And you're probably familiar with this. Your electronic product has lots of switching frequencies in there, very fast, sharp digital signals, which emit very broadband radiative noise emissions and things like that. So pretty much any product, unless it's completely sealed in a metal can with nothing coming in, nothing coming out, and the metal can's 100% effective over the whole frequency range, or the desired frequency range, then pretty much your product is going to radiate electromagnetic interference out. All those little PCB traces, everything inside acting as little antennas, and woof, out it comes. And we're not going to look at this one today, but that is the major one that everyone thinks about and is a big deal with EMC compliance. But the other one fewer people know about is conductive emissions, and many products will have to be tested for conductive emissions as well, and this is what we'll cover today. There are two others, of course. There's capacitive coupling from your source to your victim over here, as it's called, and there's also inductive coupling as well. But because inductive and capacitive coupling are near field effects, pretty much they are only they're only required to meet some sort of standard in very specific cases for products. So most products will not be tested for these near-field effects, but they will be tested for radiative interference and or emissions and conductive emissions. So even if your product was battery powered like this inside a nice die-cast metal chassis like this, and you know it's got the lid sealed on and everything, well, in theory, then you wouldn't have any radiated emissions or conductive emissions because there's no cables coming in and out of it. But that's not a very useful product, is it? Usually there's got to be cutouts for screens and things like that, so it can actually radiate signals out. Or in this case, even if we had something like this and it was completely shielded like that, bingo, we've just broken that shield with our BNC here, and noise from inside, any switching noise, can couple onto the signal and onto the coax, and bingo, out it comes. And that's called conductive emissions because it's conducting along the copper cables into and out of your product. And take, for example, the mains plug pack here. If this could be completely metal shielded till the cows come home, and you know it may not have any radiative emissions to speak of really, but you've got the mains cable coming in and you've got the DC power cable coming out. So in that case, if this was completely shielded for radiative stuff, your conductive stuff could kill you and you might fail your compliance testing. So to do conductive pre-compliance testing, we need one of these listens or line impedance stabilization network, and I'll explain why it's called that in a second. This one is from TechBox, and send it in. It is open source hardware, brilliant. And here's the schematic. I'll provide the link down below, and you can buy it from them or you can make your own. So what this is designed to do is insert in series with your power cable coming in, and your power comes in here, and then this end here these two terminals plug into your product. And what it does is it AC couples off the signal into your spectrum analyzer there, and this inductive filter here basically provides a fixed impedance, hence the name line impedance stabilization network, because basically your supply over here is an unknown impedance. You don't know what that's going to be. It could vary or whatever. It's no good, especially when you're doing standards testing, if your source varies. So all these compliance testing standards specify a specific 50 ohm network like this. So this is what it does. This provides a fixed 50 ohm line impedance that you can do a controlled testing over a specific frequency range, which we'll see in a minute, and it just taps off the AC signal. And a good listen device like this one will also contain surge suppression as well. We've got some 5 volt TVS diodes in here to protect our spectrum analyzer from any surges on the power supply here, and there's a gas discharge tube and a MOV over here, so it's pretty well protected. Otherwise, you've got to be careful when you power up your product. If it's connected to your delicate RF input of your spectrum analyzer here, you know how it's always got that maximum value. This one's pretty good at 50 volts at DC maximum, but some of them you've got to be real careful you don't blow your expensive spectrum analyzer. And there are various standards for these line impedance stabilization networks. One of them is the CISPA standard here, and you can see that the standard actually provides what the impedance of this listen network is supposed to be. Here's the upper and lower limits, and you can see this one is actually designed to fit fairly much in the middle of that, so this one actually meets the requirements. So having a standards compliant listen box like this, absolutely essential for any conductive emissions pre-compliance testing. Now a proper EMC compliance test facility will have a proper shielded room to do all this in. They'll thoroughly meet the requirements. They know what they're doing. But if you're doing simple pre-compliance in your lab, then this is a basic best practice way to do it, and the standards do actually specify this and dimensions and things like that. But you start out with basically a horizontal and a vertical ground plane. At the very least, you should be using a horizontal ground plane like this with your device under test up on an insulated wooden some sort of insulated table like this. There are, as I said, standards for, it must be X distance away from the planes and, things like that. But at least one horizontal ground plane on the bottom. You don't necessarily have to use the vertical one. These ground planes just stop capacitive coupling to other devices and things like that in the room. And then you've got your listen device down here, very short, low impedance coupling, because if that's a high impedance, if you use a big long lead on there, then that isn't a very good grounding point over the frequency range. So it has to be very short, very closely connected to that ground plane. Device under test, isolated, and then you tap off to your spectrum analyzer. In a proper EMC facility, this would be outside of the shielded chamber and things like that, but we won't go into details. All right, now what we're going to test here, very simply, very crude, so don't hold me to task over this, okay? It's just an example of pre-compliance, basic pre-compliance testing. Little USB charger, one of these crappy little USB chargers in a non-shielded box, so it's going to be radiating stuff, but of course we're only going to be testing the conducted emissions of this thing. And I've got myself a ground plane, although in this instance it's really not going to matter much at all. You can do it basic testing without a ground plane. And we've got a power supply up here. There we go, that powers our 12 volts, goes into the source part of our listen box here, and we've got our coax coming out to our spectrum analyzer there, Rigol DSA 815, and we'll show you how to set that up. And this just mounted above the ground plane here by a certain amount, otherwise you just rip out the ground plane and put it on the bench. And I've got the ground, the source point of, you don't want to ground this side here, you want to ground the source side to your grounding plate on the bottom. So that's the setup. Now I'll show the spectrum analyzer setup in a minute, but as you can see, we are getting a spike here. Now I've got it disconnected, so it's not powered at all, but it is, still connected through to the device under test side of this. And you'll notice that we're getting a spike here. That's we're going from 150 kilohertz to 30 megahertz span at the moment. So that's like 25 megahertz or something. And if I disconnect this, we'll find that there we go, it vanishes. So that now we've disconnected it, we can get ourselves a baseline. Although you can see how at the low end over here it is. We do have some noise right down at the low end there. And if we disconnect our coax from our listen device, there we go, that's our noise floor. So you can take that noise floor as a reference and actually subtract that out later if you want to, but we're not going to bother with that today. Alright, so here's how to crudely set up our spectrum analyzer for this basic pre-compliance testing. It will, of course, depend entirely upon your device under test, your test setup, what version of the standard you're using, etc, etc. But I'll show you a basic one. Basic one would be 150 kilohertz to 30 megahertz frequency range. So the first thing we want to do is go into frequency there. The start frequency, we want 150 kilohertz down there, and our stop frequency is 30 megahertz already set up. Now we also want to go into our bandwidth detect there, and our resolution bandwidth, we want to go into that. So there it is, currently set to 9 kilohertz. That's what we want it set to for this basic frequency range. Now the filter type here, Gaussian or EMI, this spectrum analyzer has a specific EMI filter which we want to use if we have it. I think it might even be a software optional extra, but you don't necessarily have to do that if you're using the Gaussian filter, as we'll see in a minute. And if we go into amplitude, we don't want any input attenuator at all at this stage, so we'll leave that set to 0 dB. And the other really important thing is our detector type there. For very quick first pass measurements, you want to send it to positive peak there. Quasi peak is what we're going to do for more detailed measurements of this thing, which takes a lot longer to scan and give you a result. But the positive peak, that's what we want with our EMI filter if you have it. And what that positive peak detection type is going to do is basically going to give you the worst case at each frequency point, the worst case value, and that's really all we care about. Does it go over the limit or not? That's pretty much it. Now for the CISPA standard EMI testing, the units are always going to be in dB microvolts, so we want that set up. So our vertical scale there is 0 dB reference point is 1 microvolt. So for example, if we're getting 1 millivolt, a signal was 1 millivolt in amplitude, then that would be 60 dB above up there. So our reference line's down there. This is our inherent noise floor of our spectrum analyzer setup here, and I think we're ready to go. Almost. Now, one thing we can do to see if we're passing or failing a basic limit is to set a reference level up here to show us whether or not we're pass failing. We can do that on this spectrum analyzer. All spectrum analyzers are different. Some will have it, some won't. I can go into trace pass fail here. I've already set it up, so I won't bore you with the details, but I'll turn it on, and basically it gives us a reference line there. And the CISPA 25 standard, just a generic one. Won't go into details, but it's basically 1 millivolt reference level across this particular frequency range. So 1 millivolt, as the example I used before, is 60 dB. So we want to go into the setup there, and you can edit these data points, and the amplitude there it is, 60 dB is our reference level at the upper and lower frequencies. So it draws a straight line. You can actually set like an envelope in there, but we just want a straight line basically. So here's our waveform, and that, if it goes over, when we turn this thing on, if our signal goes over that purple line there, warning, Will Robinson, where we could be exceeding our limit. So this spectrum analyzer pass-fail thing's actually quite good. We can go in there, set upper and lower limits, but as you can see, I've got 60 dB, which is the 1 millivolt, dB microvolts, which is the 1 millivolt level, crude by the standard here, and we can set those at both points, and now we are ready to go. We're ready to turn this sucker on. So here's our noise floor. I'll connect my coax to the listen device and still haven't applied power, and you can see that right at the low frequency down in there it's jumped up, and you can go have a look at that. But anyway, here we go. I've got a 12 volt supply here. I'm going to plug in my USB charger and let's see what we get. Once again, from 150 kilohertz to 30 megahertz with our CISPA 25 standard limit of 1 millivolt. I'm going to plug her in. Ta-da! Look at that. Once again, we got that peak that we saw before, and you can see there's a bit more broadband noise up at the high end there, you know, that 20 to 30 megahertz region up there. But, you know, there's the standard, so, you know, we're well below that. Look, and I'll disconnect my coax again so you can see that. So you can see that's our noise floor of our system, and then it jumped up just a bit at the high end. But what really concerns us is this low end down here, which is above that purple line. So we're in trouble down at the low frequency, down at, you know, the hundreds of kilohertz to a megahertz range. So we want to zoom into that and see what's happening. So I've got my marker there, and you probably can't see it. It's obscuring it a bit, bad positioning there, but you know, 4 megahertz, something like that. So it's up to a couple of megahertz. There's my marker point, so 2 megahertz. So let's go from, say, 0 to 5 or something like that, and we'll be able to see that down there. So we'll go into frequency, and our stop frequency will change that to 5 megahertz. And now we can get in there and we can see. Now you can see that, you know, it's not, we're getting close to our limit, but the average value in there is not, you know, hugely above that line. We're close, and a couple of peaks are going over. Now it's time, because this is a very quick update in using that positive peak detector. Now we want to go into our quasi detector. So we'll go here and we'll go into our quasi peak detector, and this one will actually take some time. Twiddle our thumbs, but we'll eventually get a result. And the problem there was, if we go into a sweep, it's set it to 970 seconds. That's why we're going to have to wait a while. And if we set it manually to 60 seconds, we can see it start sweeping across here, but this isn't going to be accurate. So that is certainly going to take a while. As you can see, we've gotten this far after, well, 2.5 minutes. It's going to take about 16 minutes to do that entire sweep at the recommended value of the sweep speed of 970 seconds there. That one took a bit of time, so what I've done is I've changed my frequency range from 0 hertz to 1 megahertz here, and that's giving me a sweep time, auto sweep time of 200 seconds, much more reasonable. And as you can see, we are with the quasi peak detector, we are going above our line there, our reference line, and you notice our reference line jumps up there. That's because I set it to 150 kilohertz. I should have set it to 0 and it would have gone all the way across. But anyway, the range as far as the standard is concerned is only from, in this particular case, is 150 kilohertz upwards. So even up to a megahertz here, as you can see, we're basically still over that nominal CISPA limit. So really, we probably want to take it out to a couple of megahertz again and see where it actually falls below that. But we're definitely pushing our luck here, that's for sure, with this design. And I should point out that something like this cheap, low-end general-purpose spectrum analyzer isn't quite going to give exactly the same results as a proper EMC house would with their $50,000, EMC measurement receiver. But, we can get a reasonable indication, and that's the whole idea, that this thing allows you to do some basic in-house testings, cheap and easily. Basically, it's just your time inside the house plus a $1,500 or less analyzer, not much at all, and you can do this basic testing, and most importantly, you can actually test things before and after you make changes to the product. So we're almost there for a 300 megahertz span using quasi peak detect here, and as you can see, it's starting to drop off there, and I can set a marker here. Where's our marker value? So anything sort of that point there, sorry, it's a bit hard to see with the tiny little font on this thing, but anyway, around about 2.3, let's say 2.5 megahertz and under, that's where we're probably going to be a bit concerned about that sort of stuff. So we might want to look at our design and go, well, what can we improve down at that low end? But as we saw with the wider frequency sweep before, anything like above that 2.5 megahertz, it just drops off, and it seems to be just fine. And there it is, exactly the same shot, but back in the real time there. So we're a bit concerned here with our pre-compliance testing down at the low frequency here. There's a good chance we may not pass the standard here. And what can we do about it? Let's say this thing, it's got to ship next week. We can't respin this board and add, ferrites on the output and do other stuff to reduce the EMI, change the slew rate of signals inside, tighten up the PCB layout, all that sort of stuff. What can we do? Well, we can probably try adding on one of these ferrites, one of these external clamp type ferrites. You may have seen these on products, and these are a common technique for just this thing where, well, your product's finished, oh no, but we failed our compliance testing, we still want to ship this thing. So what you can do is just add a couple of these to your power wires on the output. You may have seen them, and they may have been like a heat shrunk on the outside, for example, added after the fact to make your product pass that EMC compliance. So let's see if it makes a difference. Here's our live display here. And let me clamp it over once, and we probably, with only one, so we've only got like one turn in there, we really don't expect to see any drop at all in that, right? Not much at all. But if we wrap it around that a couple of times on just this one lead here, I think we might be in luck. So there you go, I've got a couple of turns inside that thing, and bingo, look, it's dropped us down a hell of a lot. You can see that by adding an extra turn in there, we're almost under, even right down at the bottom end there. So we're doing pretty good. Let's add another one to the negative line here. Alright, here we go. Let's see if we can see this change live. I'll just clamp this over on my negative line there, and look at that. Oh, beauty. So that's not exactly the best solution to your problem here. If you can fix it inside your product, you certainly would if you had the time to, respin. That's why you do the in-house testing. The in-house pre-compliance testing at the design stage, at the prototype stage, allows you to get a quick ballpark indication of whether or not you're going to pass this, pass EMC compliance, whether or not you're on the border. And when you're doing simple bench testing like this, even the ground plane isn't going to save you really. Just be careful about external electromagnetic fields here, which can radiate into your test system. That's why these things are done in proper shielded enclosures, things like that. We're just mucking around here on the bench doing some basic testing. As we've seen before, my LED lights above me that I use for shooting, watch this, if I get rid of them, we'll probably see this higher end broadband noise disappear. or lower. Look at that. And I'll switch it. That spike is still there. Switch it on and see. So just be careful about what things are radiating into your test system here, or capacitive or inductive coupling. Just be aware of it. And if you're wondering, does this metal shield make a big difference in this particular installation? No, not really. Let me remove it live here. Oh, there we go. A bit more higher broadband noise there, but you know, essentially it's not going to change the issue that we had at the lower end. And of course, radiated testing would be a whole different ball game again, and that requires a calibrated antenna which you connect up to your spectrum analyzer in a shielded anechoic room. I've done videos on those before, those indoor test sites for EMC compliance, which I should link in down below actually. But this one was just a basic video to show you how you can do some basic conducted pre-compliance measurements. And the good thing is that you can do these measurements even though if they're not, you know, absolutely correct to the absolute value. You can see if you're getting anywhere close to the standard, to the standards limit or not, and if you are, then you can make changes to your product and then rerun the exact same test setup in-house. Doesn't cost you much to spin a new design and add a little, you know, like you might put some little ferrite beads in there, you might do this or that, you might shield this or that, or do something, and then you can see the changes that in your product, what they make to your conducted and your radiated emissions as well. So it's really, you know, one of those vital things, in-house EMC pre-compliance, because it's much cheaper to do it in-house at the design stage than it is to get a report back, wah, failed. So there you go, there's a very brief look at some basic in-house EMC pre-compliance testing. And please don't take this video as gospel, because the standard is incredibly complex and it depends a hell of a lot on your device under test and all sorts of stuff. So, you know, and the test setups and the frequency range and the type and your product and the different classes of product that you can have within the standard. So this might be, you know, a class 4 or a class 3 standard or something like that, depending on what value it actually meets and the market you intend to sell into, and etc, etc. But anyway, there's, I'm sure, a lot of people with a ton of EMC experience will no doubt point out some really good links on the forum and in the comments. So if you do have those, please add them. Hope you enjoyed it. Catch you next time.